Welcome to this tutorial on building a fraud detection system using Java. Today, we're going to uncover the techniques and methods used to detect fraudulent activities in various applications. By the end of this series, you'll have a robust understanding of how to implement a basic fraud detection system from scratch. Let's dive in. First, we need to understand the objectives of our fraud detection system. We'll focus on detecting anomalies in transaction data, identifying patterns, and flagging suspicious activities. Our system will utilize simple heuristics and machine learning techniques for detection. Let's start by setting up our environment. We're going to require Java Development Kit, JDK, Maven for dependency management, and an integrated development environment, IDE, like IntelliJ IDEA or Eclipse. Ensure you have these tools installed before we proceed. Now, let's create a new Maven project. Open your IDE and create a new project, making sure to select Maven. Set your group ID to com.example and artifact ID to fraud detection system. Inside your newly created project, let's set up our project structure. We will need the following directories: src/main/java for our source code, and src/main/resources for configuration files. Now, let's create a transaction class that will represent our transaction data. In the transaction class, we have attributes such as ID, amount, type, and timestamp. Next, we will create a fraud detector class that will process transactions and apply rules to determine whether they should be flagged as fraudulent. In our fraud detector class, we maintain a list of transactions and have a method detect fraud which will eventually hold our detection logic. Now, let's dive into the fraud detection criteria. We will implement a simple rule that flags transactions above a certain threshold amount as potentially fraudulent. Here we've implemented a basic rule where if a transaction exceeds $1,000, it gets flagged. Let's test our implementation. We'll create a small main method to simulate transactions and evaluate whether our fraud detection works as expected. In the main class, we create an instance of fraud detector, add a couple of transactions, one of which is above the threshold. When we run this code, we should see the output indicating that a fraudulent transaction has been detected. Let's execute this program now. Great! As you can see, our system successfully identified a fraudulent transaction based on the threshold rule we implemented. This brings us to the next step, enhancing our detection with additional criteria. In the next phase, we'll consider the transaction type and frequency. We will now modify our detect fraud method to include a check for transaction types. For instance, we may want to flag multiple credit transactions within a short time frame as suspicious. Let's implement this logic. In the updated detect fraud method, we've added a placeholder for checking frequent transactions. Now let's implement the check frequent transactions method to identify rapid transactions of the same type. Here, the check frequent transactions method compares each transaction with every other transaction following it, identifying cases where the same transaction type occurs within the specified time window. Next, we need to parse timestamps accurately. We'll modify our transaction class accordingly. With our timestamp parsing in place, let's test the enhanced system again. We'll create transactions with varying timestamps to check our detection logic. As we run the above code, the system should rightly identify suspicious repeated credit transactions that occurred within a short time frame. Let's go ahead and execute it. Remember the importance of extending your criteria to refine accuracy. Having seen our program in action, it's time to document the results and refine further. In real-world systems, we would ideally incorporate machine learning algorithms to dynamically identify fraudulent patterns from historical data instead of hard-coded rules. Next, let's discuss how we could leverage popular Java libraries like Weka, DL4J, or even DL4J for deep learning to enhance our model. Before we do that, make sure you include the necessary dependencies in your pom.xml file. By now, you should have a clear understanding of how our foundational fraud detection system operates. Next, we'll investigate how to implement a simple machine learning classifier using Weka to classify transactions based on historical data. Let's create a data set representing past transactions, which will help our classifier learn. We'll structure it in CSV format. Feel free to manually create a CSV file named transactions.csv in the resources folder. The CSV should look like this, with headers, ID, amount, type, is fraud. Next, let's create a method to read this CSV data and convert it into a format suitable for our model. We will use Weka's API to load the dataset and prepare it for training our classifier. The load data method leverages Weka's data source class to pull the dataset from our CSV file. After loading, we need to specify the index of the class attribute, which will be our isFraud column. We're now ready to create and train a machine learning classifier. We'll utilize a simple decision tree classifier with this dataset. This approach is beneficial for our fraud detection as it interprets rules based on feature splits. Let's define the classifier method. In the train classifier method, we create an instance of the J48 classifier. Once it has been built using our dataset, we print the resultant model to understand the rules that the classifier has developed. Let's integrate this into our main class and examine results. Let's run this program and review the decision tree model that has been generated based on the training data. Keep in mind the importance of evaluating model performance. In practical systems, you would want to split your dataset into training and testing. To incorporate model evaluation, we can use the Weka's evaluation class to assess our classifier's effectiveness. We could compute metrics such as precision, recall, and F1 score. Here, the evaluate model method uses Weka's evaluation utilities to assess the performance of our classifier on the test data, executing methods to output a comprehensive summary of key metrics. Excellent! Running the above code gives us a full summary of our model performance based on our dataset, enabling us to assess its reliability in identifying fraudulent transactions. This is a crucial step in any machine learning application. In a real-world setting, we would continuously iterate on our model, incorporate new data, and refine our rules based on feedback and observed results. Always remember to save your trained models for later use in production. The save model method uses Weka's serialization helper to write our trained classifier to a file for future use. Proper model management is key to maintaining performance over time. And that's how you save your trained model to be reused without needing to retrain it each time. As we wrap up this tutorial, let's summarize the journey we took together. We built a basic fraud detection system using heuristic methods and enhanced it with machine learning techniques. We explored the importance of maintaining model accuracy, performing evaluations, and even extending our system's capabilities using Java libraries. You are now equipped to build on these concepts with your projects and explore more advanced methods for detecting fraud. Thanks for joining me today.